Rust is a fascinating language. It's just as fast as C or C++, it gives you just as much low-level control, and yet it guarantees your program is completely memory safe and thread safe. My previous video explains how that's possible, so if you missed that one, go back and watch that first. It's number 1 in the channel. It's called Why Rust is Safe. In that video, I could get away with a bit of hand-waving because we were dealing with a made-up thought experiment language. But starting today, we're talking about a very real language. This video is about the most basic bits of Rust syntax. Functions, variables, conditionals, loops. These are concepts you already know, so we're going to go pretty fast, and I'll leave you with a little coding exercise to practice what you've learned. To guarantee memory safety, Rust also has to be completely type safe. And to make that work, there are many details in the language that have to work together. Ownership and borrowing are important, but they're not the whole story. Even in the Scalar types, there are some interesting details around casting and type safety of Unicode characters of all things. Curious? Alright, we've got to start somewhere, so here it is. Hello world. If you'd like to follow along, you can run this for yourself in the Rust playground on the web at play.rustlang.org. What do you notice so far? Functions are introduced by the fun keyword, and execution begins with the main function. And we have curly braces and semicolons. This is a civilized language, thank you very much. No semantic white space here. The most obvious odd thing so far is that exclamation mark. That tells us println is not actually a function. It's... Okay, I'm going to tell you something, and if you're a C programmer, I want you to stay with me here, okay? Just hear me out. Println is a macro. Now, in C, macros are terrible. They're implemented by something called the preprocessor, which doesn't know anything about C syntax. It just takes a stream of source code text and does cut and paste with it, and then feeds that to the real compiler. And a macro invocation looks exactly like normal code, so it's far too easy to do really evil things by accident, like breaking operator precedence with really surprising results. What's more, macros are basically the glue that gets used to fill all the gaps in the language, so it's a whole thing. In Rust, macros are nothing like that. Macros are part of the grammar of the language, and they operate at the level of the abstract syntax tree, not the source code text. So the definition of a macro will say, this argument must be an identifier, or this argument must be a complete expression, and an invocation won't compile if it doesn't get what it expects. If a macro uses local variables, those are in a separate namespace, so it's not possible to have name collisions. This kind of system is called hygienic macros, and it enables some quite powerful metaprogramming. That'll be another whole video one day. The reason println is a macro is because it takes a variable number of arguments, and it parses the format string at compile time and checks it against the types of the arguments. So let's try that now. Let's declare a variable and print its value. The let keyword declares the variable x with type u32. The thing after the colon is the type. u32 is the unsigned 32-bit integer type. In the println format string, the pair of curly braces is a placeholder, and that gets substituted with the value of x when this runs. So this program prints out x is 10. Rust is a statically typed language, just like C or C++. That means the type of every variable is nailed down at compile time. The word static just means not changing, so once a variable has a type, that type never changes. In this case, we're explicitly declaring the type of x to be u32. We don't have to specify the type, we can instead let it be inferred by the compiler. This syntax 10u32 probably looks a bit unusual. It's the literal value 10 with the explicit type u32 specified in the literal. I'm assigning that value to x, so the compiler infers that x must have the type u32. By default, variables are immutable or read-only. Once a variable is initialized, if you want to change its value, then it needs to be declared as mutable with the mute keyword. So by saying let mute, x is now mutable and we can assign to it. The reason for preferring immutability by default is just that it makes code a bit easier to read and understand. If you have an immutable variable that's initialized with some value, you can read the rest of the function and know that value won't change. You might also be wondering why it takes two keywords to declare a mutable variable. Why not say something like var x equals 10? Well, the reason is that a let statement can declare multiple variable bindings, and each one can either be mutable or immutable. And we'll see examples of that when we get to tuples in the next video. In this example, I didn't specify a type for x anywhere, except we know it has to be an integer of some sort because we're giving it the value 10. In this case, the compiler uses the default integer type, which happens to be a signed 32-bit type called i32. These are Rust's integer types. U means unsigned, I means signed integer. We have 8-bit, 16-bit, 32-bit, 64-bit, and 128-bit integer types. We also have usize and isize. These have the same number of bits as a pointer. So on a 32-bit system, usize and isize are 32-bit integers, and on a 64-bit system, they're 64 bits. Usize is the type we use to index into arrays and count lengths of arrays, because it'll always be big enough to handle the length of anything we can hold in memory. Usize gets used way more than isize. Next, we have floating point types F32 and F64. These are the standard types defined by IEEE 754. Obviously, F32 is the 32-bit floating point type, and F64 is the 64-bit one. These are equivalent to float and double in C. They take values with a decimal point. For really big or really small values, you can also do the scientific notation thing with an E. So 6.022E28 means 6.022 times 10 to the power of 28. We also have a Boolean type called bool with the values true and false. True and false are keywords. A bool is 1 byte in size, but it only ever holds one of these two values, which are represented as 0 and 1. It's undefined behavior to create a bool containing some other value, but you don't need to worry because that's not possible in Safe Rust. And finally, we have a type called char, which is, of course, a Unicode scalar value. You all know what a Unicode scalar value is, right? Of course you do. It's basically a Unicode code point, but without the weird surrogate code points that were invented to make UTF-16 work. We don't need surrogates. Rust has great support for UTF-8. So in Rust, a char is always 32 bits in size, but only certain value ranges are allowed. It's undefined behavior to create a char with an illegal value, but again, that's not possible in Safe Rust. Char literals are written in single quotes, and you can write anything that can be represented by a single code point, including lots of emojis. Some emojis need multiple code points. For example, anything with a skin tone specified is made by combining code points, so that would have to be a string, not a char. We'll get to strings eventually. So those are all the scalar types. When you need a reminder of what these types are called, you can go to rustcurious.com and click on the Elements of Rust. The scalar types are in this block on the left-hand side, and each square is a link to the official documentation for that type. The compiler will never implicitly convert between any of these types. Let me say that again. Rust will never implicitly convert between any of these scalar types. When you do want to convert between them, one way to do it is with the as keyword. So here, C is a char, and C as U32 converts it to an integer, so we can print out its decimal value. The details for casting like this between scalars depends on the types involved. So for example, I can cast from a char to a U32, but I can't cast from a U32 to a char because not all U32 values are valid char values. By the way, if I want to display that value as hex, I can change the format string. The :x inside the placeholder means use hex formatting. There are lots of options for formatting. Let's not get into all of those right now. So C as U32 is an expression that produces the value of the char as a U32. When you write an assignment, the thing on the right of the equal sign is an expression. Anywhere you can write an expression, you can write a block of code that produces a value. The value assigned to x is the value of the block surrounded by curly braces. The value comes from the final expression inside the block, so in this case a plus b. So x gets the value 30. Notice there's no semicolon after that final expression a plus b. You can think of the final expression as being the thing after the last semicolon or the last statement in that block. The point of using a block here is you can use temporary variables and as much complicated code as you like to come up with that value. Here we're just adding two variables, but you can do whatever you want. Notice we still need the semicolon after the closing curly brace to terminate the let statement. This idea that a block can result in a value also applies to the function body. This function takes a U32 called x and returns a U32. The return type is written after the arrow. Parameter types and return types for functions must always be declared explicitly. The value returned by this function is the final expression in the function body, x times 3. Again, no semicolon after that final expression. If we did write a semicolon after the x times 3, the final expression in the function would be nothing. And that would be a type mismatch because we said we'll return a U32, but we're returning nothing. Check out the compile error. Now, C++ has trained us not to read compile errors, and I want to turn that around, so let's take the time to read this one in detail. Mismatched types. Expected U32 found, and that empty pair of parens is called unit. It's the type that represents nothing. So this error says expected U32 found unit. The function implicitly returns unit as its body has no tail or return expression. And then there's a very helpful tip pointing at the x times 3. It says remove this semicolon to return this value. As you can see, the compiler team has worked hard on Rust's error messages, and they're often super helpful like this one. Sometimes the suggestions can still lead you astray, but usually they're pretty good. Okay, let's do conditionals. Unlike C, the condition does not need to be surrounded by parens. The condition expression must evaluate to a bool, which of course the comparison operators do. And the curly braces around the body of the if are required. They're not optional like in C. Of course, you can add an else block that executes if the condition is false. Now, here's something interesting. If-else can be used as an expression. The value of the if-else expression is the value of whichever branch is executed. This only works if you have an else block because you need to produce a value in all cases. No need for a separate ternary operator, if-else does the job. Let's use this in a function. I think we can make this code a bit simpler. We don't really need this temporary variable max. So now the if-else expression is the final expression in the function body, so its value becomes the function's return value. Rust makes it easy to write in this pure functional style, but you don't have to. You can also return early from a function if you want to. This average function wants to divide total by count, but it first checks in case count is 0 and returns early if it is. Sometimes you have many cases you want to check for, and a long chain of if, else if would be cumbersome. For that, we have match expressions. Here we have a function that takes a char and returns a description of the character. The return type is ampersand single quote static str. What the hell is that? Well, it's one of Rust's many string types, and don't worry, there's a good reason it looks like that. Strings in Rust are actually awesome. We'll talk about them properly one day soon. For now, I'll just say this is a reference to a string that's valid in any scope, and that's always true for string literals. Anyway, this function uses match. It takes an expression, in this case just the char C, and tests it against a series of patterns. Each of these lines inside the braces is a match arm with a pattern on the left and an expression on the right, separated by an arrow. And notice this arrow uses an equals sign. It's different from the arrow used for the return type of the function. So the first match arm has a pattern that matches the thumbs up emoji, and if C matches that, then the string with the word like is the result of the match expression. The next match arm has a pattern with a bell, and of course it returns the string subscribe. How'd that get in there? The next pattern will match the left square bracket or the right square bracket. And we just keep going down the list until we find a match. The first one wins. So if C is the digit 5, then we return the word 5. If it's any other digit, we return the word digit. Notice the inclusive range here with ... equals. You can combine multiple ranges into a single pattern to match lowercase or uppercase letters. And then we come to the underscore pattern. Underscore is a wildcard. It matches anything. But this match arm also has an if called a guard condition. So if we cast C to an integer and it's less than 128, then we return other ASCII. Matching is required to be exhaustive because you have to return something for all possible cases. So the underscore wildcard in the last arm is the catch-all, the default if none of the other arms matched. In this example, the expressions on the right of the match arms are all just literal strings, but they could be any expressions, including block expressions containing code that does stuff. Of course, all the right-hand side expressions have to result in the same type, so the value can be returned from the match. Okay, that's match. You probably won't use it much with scalars, but when we get up to dealing with enum types, we'll definitely be talking some more about match expressions. It's an important part of the language. All right, hopefully no big surprises in the concepts we've seen so far. Let's look at loops. The loop keyword makes an infinite loop, and we can use the break keyword to exit the loop. In this example, I'm calling a function to generate a random value for x on each iteration, and we break out of the loop when x is greater than 200. Loops also support the continue keyword, just like in C. So of course your immediate question is, why on earth would we want a keyword for an infinite loop? Why not just use while true? Well, the answer is that an infinite loop can be an expression that produces a value when you break out of the loop. So let's say you want to keep that random value that was greater than 200. The break keyword can take an expression, in this case x, which becomes the value returned by the loop expression, which we can assign to y. Now, don't worry, Rust does also have while loops and for loops. Here's a while loop that repeats for as long as x is greater than 0. And just like if, the condition must evaluate to a bool, and it doesn't need parens around it. The curly braces are required around the loop body. And finally we come to for loops. For x in 0.10. This loop prints the numbers from 0 through 9. 0.10 is a half-open range that includes 0 and does not include 10. If I also want to include 10, I can instead use a closed range expression. With 0 ... equals 10, this now prints 0 through 10 inclusive. Ranges are just one kind of iterator. There are many. For loops work with any kind of iterator. An iterator produces a sequence of items. In this example, the range 0 ... equals 10 is the iterator, and each item is an integer. On each iteration, the next item gets assigned to x, which is only in scope inside the loop body. I'm planning a whole video on iterators, mostly about the 4 different ways to iterate through collections. We'll get there. Okay, so we've seen println, variables with let and let mute, the scalar types, i32, u32, bool, etc. Functions, conditionals with if-else, while loops, and for loops. Now, you can sit there and watch me go through all this, but unless you get that learning from your eyeballs into your fingers, it'll be gone in 10 minutes. You didn't think you could get away with just being a spectator, did you? No, it's time for you to do some work, time to learn by doing. I have a tiny little practice exercise for you. You don't need anything more than the syntax I've just shown you, and the act of actually typing it gets this understanding into a different part of your brain versus just seeing code on the screen. You don't even need to install a compiler. You can do this in the Rust playground on the web. And I've already set up the playground with unit tests for you. So just go to rustcurious.com/2. That'll take you to the page for this video. And then scroll down to the exercise and, oh, hang on, what's this? Boost your learning. For purchase. Lesson 3, Panic. Learn how to manage unrecoverable errors in Rust. Division by zero, integer overflow, out of bounds array access, and failed assertions. Cool, I'll definitely have to come back and watch that. And I really want to push that red button, but okay, first I should try this exercise. So, there's the source code, but I can just press open in Playground and there it is, ready to run. This exercise is about the factorial function. So just a reminder, factorial of 5 is 1 times 2 times 3 times 4 times 5. And this playground already comes with an implementation of factorial. It takes the argument n, and if n is greater than 1, then it multiplies it by factorial of n minus 1. So this function is recursive. It calls itself. If n is 5, it will return n times factorial of 4, and so on. If n is 1 or 0, it just returns 1, which is correct according to the definition of factorial. And if I scroll down, we see there's a comment that says we don't have to change anything below this line. And there's a main function and a test function. So up the top, if I expand the 3 dots menu, there's a whole bunch of options for what I want the playground to do. If I select run, then it's going to compile the program and then run the main function. So let's do that. And we see it's printed out factorial of all the values from 0 up to 20. Factorials get pretty big. Now let's look at that test function. It's called test factorial and it has this line above it that says hash test. This hash square bracket syntax is called an attribute and it applies to whatever comes immediately after it, in this case the function. The test attribute says this function is a unit test. So now when you compile your code normally, all the test functions are left out. But if you say you want to build a test runner, then all the test functions are compiled in, and the test runner invokes them all and checks they pass. You can have as many test functions as you want sprinkled around your code. This makes it easy to keep the tests close to the code they exercise. This test function calls factorial with different values, and it asserts that the return value is equal to the expected value. Assert equals is a macro that panics if the values are different. Panics, that's what that premium video is about. Definitely have to watch that. Anyway, if I go back to the menu and select test, I see that it compiled and ran one test, test factorial, and it passed OK. It works, it passed the tests. What's the problem? Well, right now it's recursive. It calls itself, which means it uses memory proportional to n. And no, Rust does not have a guaranteed tail call optimization. That's left up to whatever LLVM feels like doing. So we want to fix this by changing factorial to be iterative instead of recursive so that it does not call itself. Remember, factorial 5 is just 1 times 2 times 3 times 4 times 5. So your job is to delete the body of the factorial function and rewrite it with a loop and a mutable variable. You multiply together the values from 1 to n and return the result. Easy, right? Now, when you sit down to do this, if you're not sure how to start, it's probably because you're just not used to thinking in a different language yet. So just write it the way you would in a language you know well. In your favorite language, could you write a program that uses a loop to multiply some numbers together? Yeah, you've got this. Then just fiddle with the syntax until the compiler's happy and the tests pass. I'll leave these examples on the screen to remind you of some relevant syntax. In lesson 3, I'll walk through the solution to this exercise and then we'll make factorial panic. Actually, you don't have to wait, you can make it panic right now if you like. Just change the main function to show factorial of numbers up to 25 instead of 20. In that premium video, we'll dig into what it means to panic, and all the ways panics can happen, why you might choose to panic, and what it means for the safety of your program. Essentially, a panic is the simplest way to handle an error. Just stop the program. We'll look at checked arithmetic and overflows and some differences between debug builds and release builds. We'll look at converting between types when sometimes, depending on the value, that can cause an error. We'll practice using panics in unit tests, and I'll show you how to write a unit test that ensures a function panics when it's supposed to. And then we'll get into a somewhat subtle issue around how panics work when you have multiple threads. And to illustrate, I'll show you a tiny multi-threaded network service. For historical reasons, Rust's default configuration for panics with multiple threads is probably not what you want. I'll explain why and show you how to configure it properly to make your software as robust as possible. We'll also look at how code that panics interacts with other languages and how you can write your own panic handler for embedded firmware that runs without an operating system. And finally, there's another practice exercise that's still quite small, but a little bit bigger. So if you're enjoying this so far, go press that shiny red button. You know you want to. Or don't. Honestly, it's entirely optional. The series of free videos is designed to make sense whether or not you watch the premium videos. The premium stuff is really about going deeper if you're serious about learning language, or just curious and want more. Remember, the point of all this is to give you hands-on experience with Rust so you can see for yourself how the guarantees of memory safety and thread safety work out in practice. That's where we're headed. So I'll be back soon with another free video where we'll get into structs, move-only types, and how they can be used to protect resources in your program. That's it for now. Stay curious, and I'll see you soon.